This is work done as part of internship project. Enayat is a grad student from JHU, Johns Hopkins University. He was an intern with me last summer. This was his internship project, and Tung and Ryan are my colleagues at Adobe. Raman is a faculty at JHU, his Enayat's advisor. So I'll be talking about machine unlearning via algorithmic stability. Let me begin with the motivation. Motivation are the recent privacy laws, and which many people expect to get more stringent as we go on. So here are two articles from EU General Data Protection Regulation, GDPR, that came into act, I think, in 2019. And essentially, this gives users the right to ask for their data to be deleted from the company's database. And similar kind of provisions were also part of California Consumer Privacy Act. So one question is, what is deletion of data? Just deleting data from company's database may not be sufficient. This is still the definition of what exactly is deletion is a bit of gray area. So, but it might become more well-defined as we move on. But one issue with just deleting data from the database is that there are machine learning models that have been that are usually trained on the data, and when a user asks their data to be deleted, we would want to ideally update these models to reflect that that data has been deleted, that the model doesn't contain any information pertaining to that user. So a slightly formal way to say that is that if S is the data set we begin with, and Z is the data point that we need to delete, then we want an updating algorithm, which we'll be referring to as the unlearning algorithm, that takes the learned model. So A is the learning algorithm. A of S is the, say, the machine learning model that has been trained on the data set S. It takes the learned model and the data to be deleted and produces some output that is roughly same as training the model on the deleted data set. So one question is, what notion of approximation is should we use here? And there are many used in literature. A popular one is based on differential privacy. And these papers here have considered differential privacy as their notion for deletion. And in particular, I think the recent paper that was by Seth Roth and Sharifi and Malbajardi, they deal, they give algorithms, and maybe they give, this is probably the only paper I know, or the first paper that I know that gave some rigorous guarantees based on differential privacy. So what we are interested in here is a more strict notion. We want exact unlearning. So just to step back, our setup is the following. We can think of it as split into three stages. In this first stage, we have some data set S, and we want to train a machine learning algorithm on the data set A, on the data set S. And in stage 2, we get a deletion request, a point to be deleted from our data set, say Z. And we want to design and apply an unlearning algorithm that takes the learned model as well as the point to be deleted and produces a model that is approximately or in our case, in equal, we want exact unlearning, so this will be an equality, as what we would have gotten if we trained on the data set with the point removed. So one trivial solution, and this is the maybe the only one we know, is to just recompute. So we have the data set S, we remove Z from it and retrain. So that would achieve these goals. The drawback is that it is computationally expensive to retrain every time we get a deletion request. So the main goal of this work is to reduce this computational cost. Yeah, so just to define what we mean by exact unlearning, let's start with some notation here. So Z is our data domain. So our data set, data set contains, say, Z1 to Zn, and these are all part of the big data domain. The model we'll learn lies in the space W. So in the logistic regression case, say model is represented as a vector in RD. So W can be RD if there are no constraints. And we'll also sometimes need to store some metadata corresponding to the internal state of the algorithm at various snapshots at various times during the training. So what we want is a learning algorithm A that takes a data set S and produces a model as well as maybe some metadata. And the unlearning algorithm takes the model and the metadata produced by the learning algorithm and a point to be deleted, and it gives updated model and metadata. And by exact unlearning, we want these two, the output of the unlearning algorithm to be equal to the output of the training algorithm on the deleted data set in distribution. So we will have randomized algorithms, and the random variables corresponding to the unlearning algorithm and the learning algorithm are equal in distribution, which is the definition is for any set, the probability that the output of the unlearning algorithm lies in that set is same as the probability that the output of the learning algorithm lying in that set. So we'll also not just consider one deletion request. We might have a stream of edit requests, and it can be both deletion and insertions. And we'll ask for learning guarantees, the exact unlearning guarantees at each time, at each edit request. For this talk, I'll mostly assume we get just a stream of deletion requests just for simplicity. And this is also considered in previous papers. So the first paper I know that that was about machine unlearning is this paper in 2019 by Antonio, Guan, Valiant, and Zhu. And they considered a stream of deletion requests. And the paper that I mentioned earlier, the one by Seth-Roth and Malvajardi, they considered both deletions and insertions. Let me know if you have any questions at any point. So just to simplify some of the expressions, we'll also assume that we'll start with n data points and we'll get a stream of k edit requests. So the number of edit requests is k here, and at every point, the number of data points we have is bounded between n over 2 and 2n. Just to give some examples where we can do unlearning efficiently, let's consider a linear regression problem. So linear regression is, we want to learn this W, or find the W that minimizes the squared norm of xw minus y whole square. Y are the labels and x are the covariates. And if we do like the straightforward way to train it, we have a closed form expression for the minimizer, and that is some matrix here based on the covariates. This has dimension d cross d applied to a vector, which is a d cross 1 vector. Now, if we do retraining after every deletion request, we would spend time that depends on the number of data points, because to compute this matrix here, we need to spend something like order nd square time. There are n terms in this summation here, and each term is a d square matrix. We sum them all up. The main point is that we have to go over every data point once, so we spend time linear in n. And similarly for the other expression. But using just the structure of this, we can see that if we get a deletion request, say the nth data point needs to be deleted, then if we just store this d cross d matrix here, we can just remove the one data point, which just takes like a d square time, like independent of n. We don't need to look at all the data points if we have stored that matrix. And we can update both the first term and the second term. So we can do retraining or the unlearning much faster than naive retraining, which depends on n. Similarly, we can, if we have a divide and conquer structure, like say we have a bunch of data points. Those are the leaves, and we do some computations on the leaves and merge them and so on. And this is our output. And now if we want to delete a point, instead of retraining, we could, if we had stored our computations on each of these nodes, we just need to update the model on the path from that leaf to the root. So that's that would be much faster than doing a full retrain. So these use like special structure in these algorithms. What we would be interested in is in empirical risk minimization problems, the common problem, one popular approach in machine learning for convex optimization, for convex loss functions. So let me define what a convex function is. Most of you probably already know, so I'll just go over this quickly. A function is convex if its graph looks like this shape, or in other words, if you take any two data points, if you take any 2 points on the graph and connect it by a line segment, the line segment lies above the graph of the function. We'll also assume that our loss functions are Lipschitz and smooth. A function is said to be Lipschitz if the difference of the function evaluated at any 2 points, say x1 and x2, is bounded by the distance between x1 and x2. And an equivalent way of saying that, when function has gradients everywhere, is that the norm of the gradient is bounded by some constant g. And similarly, a function is said to be smooth if the gradient of the function is Lipschitz. Or in other words, the norm of the difference of the gradient evaluated at x1 and x2 is bounded by the distance between x1 and x2. Again, for simplicity, we'll assume both this constant, both this G and L are order 1. So I will hide G and L from all the expressions. So that's a convex function. And the problem we consider is the following. So we have some model space W. It's closed, bounded, and convex. Let's also assume it's just the full RD for this talk. And we have n data points to begin with. And we have a loss function, which is f, which is a function of 2 variables. And if we fix the second variable to be some z, which will be one of the data points here, then the function, which is now a function of just one variable, is both Lipschitz and smooth, and it's a convex Lipschitz smooth function. And the empirical risk minimization framework is essentially like a method which minimizes, which finds the optimal W. So we take the average function, averaged over all the data points Zj, and we want to find the optimal W here. So that's the empirical risk minimization framework, which is very popular in machine learning. And we want to find near optimal, and we measure accuracy, also referred to as excess empirical risk, as the difference between this overall loss function evaluated at the point we output from the absolute minimum of the loss function. Of the, I think the term is the risk, the empirical risk. So the common problems, linear regression, logistic regressions, all can be captured in this, and also problems beyond machine learning. And another closely related notion is the population risk minimization, where instead of summing over n data points, the data points are usually assumed to be sampled uniformly from some underlying distribution D. We take the expectation over Z. So we have this f of WZ, and we take expectation over Z. And that gives the population risk function f of W, and we want to minimize that. And we similarly define what excess population risk is. What we want, so just to summarize, so we assume f is convex, Lipschitz, and smooth. In its first argument, we start with n data points. We observe a stream of k edit requests, and at all points in our stream, we assume that the number of data points we have is sandwiched with between n over 2 and 2n. And we want to define, we want to design an algorithm, learning algorithm A, and an unlearning algorithm U, such that we have the exact unlearning property, and we output a model that is accurate, and also we can do unlearning efficiently. So what do we know? For exact unlearning, the only kind of baseline we have is just to retrain every time step. And there is a closely related notion of the most closely related work to ours is this epsilon delta differential privacy based one. And I will briefly mention some comparison with it later. So here is our main result. So for the ERM problem, so this we are assuming is order 1. So say we have a Lipschitz convex smooth function. For any parameter for any row that is positive, we get the following following guarantees for our learning and unlearning algorithm. So we have the exact unlearning as we wanted, and we can get an accuracy that is the minimum of these two terms. We get these two because we actually end up with two different algorithms. One algorithm achieves this bound and the other algorithm achieves this bound. And finally, the unlearning runtime. So if we observe K, if we get K requests, then the baseline that we have is just retrain every time. And that would take K times the training time to do this, since we have to train K times. But we can save that by a factor of rho. So think of rho as something less than 1. So we need to retrain only rho fraction of the times as compared to just retraining every time. And it also mentioned what can we say about the training algorithm, because training algorithm could be something that takes exponential time, and I'm saying the unlearning runtime in terms of the training time. But actually, our training algorithm is optimal in terms of the number of gradient computations, and it's like essentially one of the stochastic gradient descent algorithms. This means that we give a strict improvement over retraining every time. It's not like a compromise between exact unlearning and the training time in the low accuracy regime. So if we want accuracy only, that is, so if we can tolerate error that is greater than these two terms here, so 1 over square root n or the 4/5 power of square root d over n, the minimum of those two, then the unlearning runtime is strictly better than the training time by an optimal training algorithm. Not just our training algorithm, by compared to an optimal training algorithm. And this condition often captures like the regime that the machine learning problems are interested in, because usually there is a lower bound for the excess population risk. People want to minimize the excess population risk, not the excess empirical risk. And that's like the test accuracy, and that is usually lower bounded by something like 1 over square root n. So in that regime, we or close to that regime, we are strictly better than just retraining. And just to compare with the epsilon delta approximate unlearning, since there are different dimensions, we have the metric of unlearning runtime, the accuracy, and theirs is approximate unlearning, whereas ours is exact unlearning. Here is one way to compare. We fix the unlearning runtime for their algorithm and ours, and then what happens is, if their accuracy is better than ours, only for kind of meaningless epsilon delta, very bad epsilon delta parameters. I won't go much into detail. We can revisit if this is not clear. Yeah, so any questions so far? Okay, so I will move on. So here is our approach. We have, say, a data set, we start with S and we get one deletion request, and the updated data set is S prime. And our randomized learning algorithm is A. And say the output distribution is P when the learning algorithm is run on the data set S, and it's Q when it is run on S prime. So our goal is to move the distribution P to Q efficiently. So say the blue distribution here is P, and this is Q here. And we want, so what's happening? So we initially train on the data set S, say it outputs a model W, and we want an unlearning algorithm that takes that model and a data set to be deleted, and say it produces W prime. So one condition is we want W prime to be distributed like Q, which is essentially the distribution of A of S prime. And we want this computation to the unlearning computation to happen quickly, efficiently. So if we assume that if you assume the following, say there are two cases, W prime is equal to W, so we don't change the model at all, then U has zero compute. And the other case where W prime is not equal to W, then U is essentially retraining. The amount of time it spends is equivalent to retraining. Then what we have is that we want to design, we want U that maximizes this probability of being equal. W prime is equal to W. So if we look at this W comma W prime, it's a joint distribution. It's a coupling. What that means is that W is the marginal. The W is distributed as P. W prime by our requirement is distributed as Q. And we want to maximize the probability that W prime is equal to W. So that motivates us to define what we want. So we want P and Q to be close for this computation to happen efficiently. And the closeness we define is in terms of total variation distance. So total variation distance is defined as the maximum difference between the two probability, the mass of two probability distributions on any set. So total variation distance between P and Q here is the difference between the probability mass of P minus Q, and we maximize over the measurable set E. And an equivalent way of defining this is in terms of coupling that referred to earlier. Coupling is distribution over, it's a joint distribution. So in our case, say the model space is model space is W. So the coupled distribution is a distribution on this product space W cross W, and such that the marginal on any one dimension is equal to the P or Q. So there is a probability distribution P and probability distribution Q, and we want when we take the joint distribution and look at its marginal, we want it to be same as P or Q. And there is something called maximal coupling, and that is the coupling that minimizes the disagreement between X and Y. So if I sample X and Y from the coupled distribution gamma, then the probability that it disagrees will be equal to the total variation distance for a maximal for a maximal coupling. And so we want the total variation distance between P and Q to be small. And we define an algorithm is rho TV stable, rho total variation stable, if for all neighboring data sets, which are data sets which differ in, say, 1 point, say S prime is obtained from S by deleting 1 point, the total variation distance of the learning algorithm applied on S and S prime is at most rho. So here is one way to show that there is a maximal coupling. Say the two distributions P and Q, they have PDF, probability density functions. Then an easy way to construct a coupling is given here as a mixture of two distributions. So we know that with certain probability that in a maximal coupling, X will be equal to Y. And so we take a mixture weight, so 1 minus total variation between P and Q. We sample X from this expression here, which is essentially the probability distribution corresponding to the minimum of the two PDFs, so P of X and phi P of X and phi Q of X, which is the green region here. We sample X from that and set X is equal to Y. So that happens with probability 1 minus TV. And with the remaining probability, which is the TV between P and Q, we sample from a product distribution. And the product distribution is the distribution product of the distribution corresponding to this density, which is the blue minus the green region times the red region, which is the PDF of the Q minus the green region, so which is that region. So it is easy to compute that this is an overlapping. This is a mixture distribution, has the right marginal, and it constructs a maximal coupling. So what will be useful, more useful for us is constructing maximal coupling by something called rejection sampling. Rejection sampling is maybe a more constructive way to construct, do construct maximal coupling, and that the algorithm is as follows. We initially sample X from the distribution P. Then we sample a uniformly random number in this interval 0 to P of X. If the sampled random number is less than the PDF of Q at X, then we just set Y is equal to X and output X is equal to Y. So that's our that's the case when X is equal to Y. Otherwise, we sample from Q of X, and we sample also a uniformly random number from 0 to Q of X until a certain condition is satisfied, until R is bigger than the PDF of P of X. And then we output, once we have that condition, we output X comma Y. This exact thing won't be sufficient for us, because for us, what's happening is the distribution P is A of S, the output of the learning algorithm S. And when we sample, so sampling from that is essentially training on the data set S. And sampling from Q of X corresponds to doing this retraining or training on the data set, training on data set S prime. And we want to minimize that. But if we look at how many times we do this recompute, how many times we sample Y from Q of X in rejection sampling, no matter how close P and Q are, in expectation, we have to do one resample. So that would correspond to, in expectation, we have to do retraining once. So this exact algorithm won't be good for us, but a slight variant is will suffice. Okay, so here is our overall approach. We design a learning algorithm which essentially takes S and outputs an X, which corresponds to sampling from a distribution P. So it's a randomized learning algorithm. And then we want to design a coupling-based unlearning algorithm. So it takes X and outputs a point Y, such that the X comma Y is the distribution of X comma Y is a coupling distribution, and so that we can do this computation efficiently. And also the coupling constructed is maximal or near maximal, so that we because that means for us that we don't have to do recomputations. And for people who are familiar with differential privacy, the learning algorithms will look very familiar. I am not that familiar with differential privacy. So I'll briefly go over our learning algorithms. These are variants of stochastic gradient descent. So we'll have mini batch and acceleration for one algorithm. So we'll give two algorithms corresponding to the two upper bounds. And for one of the algorithms, there won't be any acceleration. It will be just mini batch stochastic gradient descent. And that algorithm is the following. So we start with some initial data, initial point W1. At each iteration, we sample a set of indices of size M uniformly randomly. There are n indices because there are n data points, and we compute a gradient, which is the gradient on this mini batch indices. We compute the average gradient, and then we take a gradient step. But also for sometimes for one of the algorithms, we add a noise term, which is a noise sampled uniformly from a spherical Gaussian. And the metadata we store for our algorithm is this information. We save all the iterates. So we save the noise term, we save the WTs and the mini batch indices and the computed gradient. Okay, so as I said, so the one algorithm corresponds to not having this term. There is no noise term. It will be just mini batch SGD. And the other algorithm will have this term, that is the noisy accelerated mini batch SGD. And we'll see a bit more detail for both. So it is 9:40, so I should hurry up. So here are the bounds we have. So in terms of row TV stability, for our when we set appropriate parameters for the algorithm in the previous slide, we get that the accuracy is 1 over square root n. This is for just mini batch SGD. And this is for the other algorithm, for the noisy SGD, we get square root d rho over n. And we also get a lower bound, which is not tight. We get that for any algorithm that is rho total variation stable, the accuracy is cannot be better than 1 over rho n. So we don't get this square root d factor, and also in high dimensions, we don't get the 1 over square root rho n. So 1 over square root rho n is the first, this is better than the second bound in very high dimensions. Okay, so let's see why these are total variation stable. So let's take the first algorithm, which is just mini batch stochastic gradient descent. All the randomness in this algorithm comes from the mini batch indices. So once we fix the BIs, the algorithm is deterministic. So if we compute what is the total variation distance between the mini batches, note that each mini batch is of size m, and there are t iterations. So there are essentially there are roughly tm different data points involved in the algorithm. So to compute the total variation distance just between, say, these mini batches, it's sufficient to see that if we do t mini batches here, what is the probability that we sample a deleted data point? So this is our mini batches on data set S. This is mini batches on data set S prime, which is S without Z. We want to compute what is the probability that when we say sample Tm random points from n points, that we sample the deleted data point, and that probability turns out to be Tm over n. So we can show that the total variation that this algorithm is total variation stable, and the parameter rho is given by Tm over n. And if you want to do the accuracy computation, like then what we can use is this convergence analysis for stochastic gradient descent algorithms. Here V is the variance of the stochastic gradient descent. And in our case, since we do m mini batches, and we assume each of the gradient term here has norm 1, the variance turns out to be 1 over m. And we know that we know from previous slide that Tm over n is rho, which implies that T is n rho over m. So we can substitute for T here and optimize eta, and what we get that this accuracy is like 1 over root rho n. And similarly for noisy GD, so I'm here considering noisy gradient descent. The same kind of analysis works for the other variants, noisy stochastic gradient descent with and without acceleration. Here, this turns out to be total variation stable, because in each time step, say in noisy gradient descent, we compute the full gradient on all n data points, and we take a gradient step with the noise term added. So this, if you just look at the second iterate, so we have W1 to WT. W1 is our initial data point. W2 is going to be some gradient term plus a noise term. And this noise term is distributed like a Gaussian whose variance is sigma square. So if you look at the two data points, the two data sets. So here, this data set, this gradient is over S. The other one is the data set is S prime. They differ by 1 over n. So we look at the average gradient. So essentially, it turns out that the W2 iterate is difference, total variation distance between two Gaussians whose variance is sigma square and whose mean differ in 1 over n. And then we know the bound, we know the total variation bound for that. It is 1 over n sigma. And we kind of have to do it over t iterations. And there are some things called adaptive composition theorems. So it says that the total, it gives us that the total variation distance between the joint distribution over all iterates scales like square root t. And for accuracy calculation, we can use the same proof as similar analysis as before. We have this convergence analysis for a stochastic gradient descent, and we substitute for t, and we know variance. The variance in this case comes only because of this Gaussian, the Gaussian term. So when you substitute and optimize over eta, we get square root d over n rho. Now let's come to the unlearning algorithm. So unlearning algorithm for accelerated stochastic gradient descent, we tries to construct a coupling between the output of dataset output on the dataset S and S prime. And for the accelerated stochastic gradient descent, there are many variables involved. There are B1s, BIs, which these are the mini batch indices, and the actual model that we output, which are the W1 to W at various iterates. So the dependency structure looks more complicated, but it helps to consider a simpler algorithm so that we don't have some of the variables. So let's just consider again the noisy gradient descent, like I showed, for which there are no mini batch indices and only WIs. And here is the algorithm. So let's just consider one step of the algorithm, noisy gradient descent. So if we consider two data sets, this is data set S and this is data set with a point removed, and we look at one step, the only thing that differs is potentially, I mean, the mean of the normal distribution. So the W2 is distributed normally, and their means are different for the two data sets. And so our algorithm is as follows. We have already trained the algorithm. We have already trained on dataset S. So we have W2s because we have saved all the states. We can compute the mean on dataset S prime using the finite sum structure. We just have to remove the gradient on the point that we delete. So if Zi is the point that we delete, we can just remove from the mean that we have already computed. So this can be computed in order 1 time instead of order n time. This is why unlearning is efficient for us. And since we assume the function is Lipschitz, we have that the means differ by at most eta over n. So we do a rejection sampling, but the main difference is that is in the second step. So we, like before, we have a sample. We have already trained on dataset S, and this is W2 is the trained algorithm on S. We sample a uniformly random number. So this is our algorithm on S. This is on S prime. So this is P, this is Q. We sample uniformly random number between this interval. Say it lies here. So it is below the red curve. Then we accept. So we output, we take the same step for the S prime. If in the other situation where the randomly sampled number U is above the red curve, then there is a way to do coupling of normal distribution, which is very efficient instead of doing this kind of iterative resampling, and that just does reflection. So we take the midpoint of the means of these two distributions, so this midpoint, and we reflect W2. So that is this. So we reflect, and we can show that this constructs a maximal coupling between the two normal distribution. And the good thing about this is the runtime is order 1, and we don't have to repeatedly resample from the distribution Q. And this constructs a maximal coupling. And in higher dimension, there are reflection samplings, which essentially, like, we take the midpoint of the two Gaussians, and we reflect around W2 around the midpoint. And there are multiple reflection samplings. We can also take the hyperplane separating the two means and reflect around, about that hyperplane. And if you are just curious what kind of coupling it constructs, the reflection-based maximal coupling between two normal distributions they have the same standard deviation but different means. The means are 1 and 0, is supported on just two lines, diagonal and antidiagonal. Not anti-diagonal, diagonal and these two lines. Whereas if you do coupling like I described it in the beginning, we get this kind of joint distribution. Okay, so in the final few minutes, I'll wrap up by saying how do we do this for across all the time iterations, and why do we need acceleration in the case of noisy gradient descent. So first, for gradient descent, noisy gradient descent, this is what we do. We couple every time step. So we go through each of the iterates, and one by one, at each time iteration, conditional on the past, we have two Gaussians. We do reflection-based maximal coupling. So we can show that the joint distribution is a coupling. But unfortunately, since we do step by step, instead of looking at the joint distribution and doing a rejection sampling on the joint distribution, we don't end up constructing a maximal coupling. So we lose a factor of square root t. And this is the reason why acceleration helps. So accelerated gradient or stochastic gradient descent has a better complexity in terms of t. So if we have a smaller t, the loss we have because of our coupling, which is not maximal, is smaller. We also do accelerated stochastic gradient descent because that has the optimal gradient computation complexity. Okay, so for stochastic gradient descent, there is one more thing to mention. There are now two kinds of variables, the mini batch indices as well as the iterates, WI. So what we do is initially we do a maximal coupling of just the mini batch indices. And it's very easy to construct maximal coupling of mini batch indices because all these B1 to BT are uniform distributions. They are all independent from each other. So we can just go over each of them. And if the deleted point, say J, is part of some mini batch, we just replace it with a uniform uniform index from the remaining data set. So that constructs the maximal coupling if we just look at the mini batch indices B1 to BI. So now there are some options. Do we do rejection sampling based on B1 to W2? That won't be feasible because kind of the total variation stability we have is only for the marginals, WIs. We don't have it for BI and WI. So then the second question is, can we do rejection sampling using just the marginals, which are like marginals W1, W2, so on. But then the marginal is actually a mixture distribution on many components. So it is tough to even evaluate it. So what we do is we just do rejection sampling based on the conditional densities. Since we have already constructed a maximal coupling of the mini batch indices, we condition on them, and then we do reflection based iterative rejection sampling. So here is the overall algorithm for noisy stochastic gradient descent. We initially couple all the mini batch indices, and then we estimate all the marginal densities, and we do rejection sampling stepwise. If we accept, we proceed to the next step. If we reject, we reflect. We do reflection at one step, and then continue to train as if we are training on the data set S prime. And what we can show is that we have a joint coupling, coupling of the joint distribution. It is not maximal coupling. We are off by a factor of square root t. So we have to do acceleration when we optimize over the parameters. We get the guarantees that I stated. And one thing to note is that even when we accept, there is in the rejection sampling, we need to verify certain things related to the conditional distributions, but we can show that we can do those evaluations efficiently. But when we have to retrain, we essentially spend as much time as when we have any rejection step, we spend as much time as a recomputation. And finally, we did some experiments on logistic regression on Mnist data. And what you can see here is a plot, the trade-off between the number of recomputations and the test accuracy. And maybe you can just look at the one noise, if you look at the noise variance. So as we increase noise variance, the number of recomputations goes down. And the test accuracy also goes down. So, but if you just look at one data point here, we just lose a bit of test accuracy, maybe 4% test accuracy, but the number of recomputations we reduce by a factor of 2 or more. And yeah, that's all. To conclude, the framework is we want a total variation stable algorithm. And that algorithm kind of has to trade off between accuracy and stability. And it should be, the training time should be optimal. And we have an associated unlearning algorithm that tries to construct a maximal coupling or an approximately maximal coupling, and which also can run efficiently. There are some open problems here, like to match upper bound with the matching lower bound. What is the best accuracy we can get for a row total variation stable algorithm, and can we construct maximal coupling instead of near maximal coupling? Yeah, that's all I had. Sorry for going over by 2 minutes. Any questions?
I don't have any questions, Anup. I think that was terrific.
Okay, cool.
You've silenced us. Thank you so much
That's
for
not good, but
thank you so much for presenting. That was wonderful. And I think if anybody thinks of questions later, they can email you. Yes?
yeah, sure.
Well, terrific. Are you going to come see us again soon?
I would like to. Yeah, whenever possible.
Excellent. Excellent. Well, thank you again. I hope everyone will join us next week for George Isophitis. He'll be presenting on the 18th.
Thank you.
Wonderful. Thanks all. Have a great day.
Thanks, you too. Bye.